So this implies that we can actually find all the other constants. So we use this very powerful equation on the maximal state, right? But what if we used it for an arbitrary state, which was not maximal? If you use it for an arbitrary state, then the left hand, then this, this term would not vanish for an arbitrary value of m. So, for an arbitrary value of m in general, what we will have is we just have lambda m bra j plus j minus lambda m ket minus lambda m bra j minus j plus lambda m. Oh, this is the left hand side. On the right hand side, I will have 2 lambda m j3 lambda m. Now it's a very easy exercise to show that this is just gives me the modulus of cm squared minus the modulus of cm plus 1 squared equals to 2m. Okay, so this is a very important equation that we are now. It is, what kind of relationship is this? Can somebody tell me? Where if I have given value, it's a recursive relationship or recursion relationship, right? Okay. Those of you who are from CSE, you know recursion as a technique one uses in programming. Okay, so we have a recursion relationship and we have a boundary value. So we should be able to solve this whole chain of constants, right? So let's put m plus 1 equal to j. If you put m plus 1 equals to j in this relationship, then we get cj mod squared minus cj mod squared and cj minus 1. Sorry, I should write it from left to right. It's not really Arabic. And on the right hand side, I will get 2. In place of m, I will put j minus 1. Okay. Now we know what cj is, cj squared is. We don't know exactly what cj is. Then cj minus 1 squared becomes, this is 2j, right? So this becomes 2j minus 1 plus 2j. So here we see that there are 2 factors of 2j. So we can write this as 2 times 2j minus 1. So this gives us the mod of cj minus 1 squared. Now, if you use the same recursion relationship and put m equals to j minus 2, then we get similarly cj minus 2 squared is equal to cj minus 1 squared plus 2j minus 2. And then using the value that we have just found out of this guy, we can write this as 2 times 2j minus 1 plus 2j minus 2. And then we see that we have another factor, another term with 2j. So we can, write 3j here. And here, what we have here is minus 1. And there was minus 2 coming from previously. So we write it suggestively like that, right? We could have added these 2 things, but we are looking for a pattern. So now by induction, So we are basically doing an induction. So by induction, we arrive at the value of Cj minus S squared, where S is a positive integer, right? Because it's counting the number of steps I'm taking, okay, in the recursion relationship. So if I take S steps, I should have, this should be factor of 2 here. And here for 2 steps, we had 3. So for S steps, we should have S plus 1. And then we should have a factor of J. And then we should have and then we should have minus 1, minus 2, minus dot, 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 minus S. Okay, is this clear how we got here? Because we are doing induction, by induction, we get after S steps, where S is a positive integer. Okay, so here we see an arithmetic series, right? And we know how to sum those things. That's one of the first things we learned in our secondary school, or well, in grade 8 or something, forget. But I still have to look it up every time I have to do it, because I don't have a good memory. So this is going to give me minus half of S times S plus 1. Okay. So if we simplify this, what do we get? We get 2 S plus 1J minus half, and 2 gives me 1, S times S plus 1. So we factor out S plus 1. So we get 2J minus S. Okay. So this is what a generic Cj minus S squared is. Now this process does not allow us to choose a phase for Cj minus S. Okay, so that's a phase that we have to choose. And that phase is related in quantum mechanics to an arbitrary phase you can associate to every state. So by convention, we choose, the phase we choose is just the positive number 1. So this gives us square root of S plus 1, 2J minus S, okay? So we just choose the phase arbitrarily. By convention, we choose it to be plus 1. So this is the value of one of those constants. Is this clear, how we got here? I'm just taking the square root of this equation. Okay, any questions so far?
So what did we choose the phase to be in this exactly?
Yeah, well, we chose it to be plus 1. We could have chosen, the thing is, this equation, I could have put e to the power I phi for any constant phi, any real constant phi, right?
Yeah.
So yeah, so I chose the phase so that's this one. Okay. And in quantum mechanics, this phase has no physical significance whatsoever, right? And so this is very, very beautiful because, the representation theory has such a great, connection with quantum mechanics. Because those of you who have taken my quantum class have seen this before, right? All right, so now we know that if you're applying J minus, at some point the sequence must terminate, right? So at, or let me say, for some value of S, say S prime, this sequence must terminate. Okay. So that means that when can that happen? If you look at this, we know that J is a we know that S is a positive integer, right? So the only way that this can go to 0 is when at some point this becomes 0, right? Okay. Because otherwise it'll just keep lowering. The lowering operator will just keep lowering and generating more and more states. So this can only happen, if this factor, which is 2j minus S prime, is the particular value where this happens, becomes 0. That means that J has to be a half of that integer where this happens. Okay. So S prime is a positive integer, right? Because it's just counting the number of steps we have to take to get to the 0, the annihilation point of the lowest state. And so S prime is a positive integer. This means that J, the highest possible value of M, right? J is the highest possible value of M. J is a half integer, is a positive half integer. Okay, so we have found the highest value of J, the highest value of M. Okay, is that clear? This is a very important point. So J can have the following values. J can be 0, it can be half, it can be 1, it can be 3 halves, it can be 2, it can be 5 halves, it can be 3, it can be 7 halves, and so on and so forth. Okay, so this is the maximum J3 eigenvalue. Okay, any questions?
I had a question from previous part. So what does this J square value, eigenvalue being not changed, have to do with the irreducibility?
It has to do the consequence of Shor's lemma.
Oh, okay.
Yeah. Because the lambda, you mean the lambda eigenvalue, right?
Yes, sir.
Yeah, the lambda eigenvalue is the eigenvalue of J squared, right? And J squared commutes with all the operators of your D algebra. And by Shor's lemma, if we are by definition, we are looking at an irreducible representation. So by Shor's lemma, that eigenvalue cannot change on this space. Okay.
Okay.
All right. So any other questions? All right, since this is the maximum eigenvalue of J of M, and M can change by 1, right? When you apply a raising operator or lowering operator. This means that M in principle can take values within limits which are positive or negative half integers, right? So for example, if you start with a highest m eigenvalue plus, say, plus half, if you apply the lowering operator, you should get 2 minus half, right? Okay, so we will find out what is the lowest eigenvalue as well. So now what we want to do is that we want to express our equation that we got, this equation, this value that we got, in terms of, the highest eigenvalue, j and m. Okay. Because, yeah. So if you now go back to our original equation, where we had j acting on those, so we had j plus acting on lambda m. Now, if I eliminate s in favor of m, then I get, and you get, this I leave as an exercise, it's just one line. You basically get, using this expression over here, you get j plus m plus 1, j minus m times lambda m plus 1. This is one of the equation you get. The other equation you get is when j minus acts on lambda of m, you get j minus m plus 1 and j plus of m, and here you have lambda m minus 1. Okay, so it's clear what I've done here? Because the highest value of m is j, right? And so for some generic state m, you applied it s times to get to m, right? So you use this equation to get rid of s and insert m instead. Okay. So then so these are the most important equations. Essentially, this is the solution of the whole problem. Well, not quite yet. We are almost there. So yeah, because although we have found the highest value of m, we haven't yet found the lowest value of m. Okay. So we know that for the lowest value of m, when m takes the lowest value, if we apply j minus on it, so the lowest value of m is, say, j prime, we should get 0. How can we get this 0? Well, we can get 0 from here. Right. So this means that this thing is essentially 0 for m equals to j prime. So that means that j minus j prime plus 1 j plus j prime is equal to 0. Okay. Now, either this factor goes to 0 or this factor goes to 0. If this factor were to go to 0, then that would imply that j prime is j plus 1. but this is the lowest possible value of m, and this is the highest possible value of m. So this is not allowed, right? This would violate our assumption that j is the highest m value. So it means that lowest possible value of m, j prime must be minus the highest possible value of m. Okay, so this means that if j is given for a given value of m, for a given value of j, the values of the allowed values of m are, well, m starts at j, and as you apply lowering operator, the value of j changes by 1 unit, and it can only go up down to minus j. So the one before minus j must be 1 up, and the one before that must be 2 up, right? So these are the possible value of m. Values of m. Is that clear? Any questions? Okay, so let's draw this whole thing as a ladder. So I'm going to take the ladder and put it on its side just for convenience. So here we have the highest weight state, which is lambda j. Now, if I apply j plus to this, then we get 0. Now, if I apply j minus to it, I get lambda j minus 1. And if I apply j minus to it again, I go down, dot, 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 until I get to lambda minus j plus 1, which I get to, again, j minus 1. And if I apply another j minus to it, I get lambda of minus j, and another j minus gives me 0. Okay. Now, if I take this lowest weight state and apply j plus to it, then I get to this one, and if I get j plus, so j plus takes me this way. Okay, so this is basically, the ladder we had before, but there we just we now have the explicit value of m in terms of j. Okay.